talk about acids and bases. There are various concepts by which we can define what an acid is or a base is, but the concept which we are going to explore today is Lowry-Bronsted concept of acids and bases, or Bronsted Lowry concept of acids and bases. So we'll try to define acids and bases using this concept. So according to this concept, Bronsted Lowry concept, acid is anything which has the capability of donating protons, a proton or more than one proton. By proton we mean H positive ion, because we know that hydrogen's atomic number is 1, so it has one proton in it and one electron, one proton, one electron in the hydrogen atom. This is hydrogen atom. Okay, but of this hydrogen atom, if you remove one electron, so what is left is only one proton. So that is why H positive ion is called a proton. So anything which has the capability of donating a proton or more than one protons, that's called an acid. Now what is a base? Base is something which has the capability of accepting proton or protons. Okay, acid donates protons, base accepts protons. Now let's see this with an example. Suppose you have a species HA. So this is any hypothetical species HA, where H represents hydrogen and A represents, say, an acid, acid anion. Okay, so just say that this is a species HA which reacts with the species B negative. Okay, and this B negative, B is having a negative charge, it goes, just a moment, so it goes and attacks onto the H positive, and these electrons which are shared between hydrogen and A species, they are pushed onto A. So B is taking, since B is negative, so it is taking H as a positive thing. Okay, not the electrons of the H, only H as H positive ion. Fine. So what we get is BH plus A, and since these electrons if I say these, I am highlighting them in pink, so these electrons are pushed onto A. One of the electrons was already from A, the other one is coming from H, so that's why A develops a negative charge. Okay, so this is by arrows. I explained how an acid-base reaction takes place. Now let's see who is acid and who is base. So HA is giving its proton to B. So obviously HA is acting as an acid. B negative is taking or accepting the protons. So it is acting as a base. Okay. So this is called acid-base reaction. Now, if you look at this species, which is BH, this is formed when the B negative, which is base, accepts the proton. This species is called conjugate acid of B negative. Okay, and A negative is formed when HA loses its proton. So this is called conjugate base of HA. Okay, conjugate acids and bases, they always exist in pairs. So this is the conjugate, this is the acid, and this is its conjugate base. Fine. On similar line, this is the base and this is its conjugate acid. So they always exist in pairs and they always differ by one H positive ion. Conjugate acid base pairs conjugate acid base pairs differ by an H positive ion. Okay, if you compare HA with A negative, they differ by one H positive ion. The only difference is of H positive ion. Similarly, if you compare base B negative with the BH, they also differ by one H positive ion. Fine. So let's take one example. Suppose you have HCl and you dissolve this in water. Okay, water is H2O. Now what is happening here is this O negative, the lone pairs, they take the H as H positive. The arrow always go from electrons towards the positive. Arrow shows the movement of electrons. So these electrons are pushed onto chlorine. So the reaction would look like chloride ion plus H3O positive ion. This is called hydronium ion. Okay, it's called hydronium ion. So this is acting. Now let's see who is acting as an acid. So HCl is giving its proton, so it is acting as an acid. Water is accepting the proton, is acting as a base. Chloride is formed from HCl by the loss of H positive ion. So this is the conjugate base of HCl. Hydronium ion is formed when water has taken the proton. So this is the conjugate acid of water. Okay, fine. So this is how you show these things. Now I just want to bring your attention to one of the things which I have shown in the general example. In the general example, what I have done is I have used an arrow for showing reversibility. While here in the example of HCl, I just put a reaction arrow which is showing in the forward direction. So this can be explained like if there are two reactions, like A plus B gives rise to C and D. Okay, so this arrow is the arrow of reversibility, which shows that the rate of the forward reaction is equal to the rate of the backward reaction. But suppose the forward reaction is more favored, then we show it by lengthening that arrow and shortening the other arrow. This shows that products are favored, or C and D are favored over A and B. Products are favored. Okay, products are favored. And suppose I show it by shortening this and lengthening the other. This shows that reactants are favored, or the backward reaction is favored. Fine. Sometimes the reaction is so much favored towards the products that we replace the arrow of reversibility with the forward arrow only, as shown in the case of HCl. And from there come the definition of a strong acid. A strong acid is something which is almost 100% dissociated, completely dissociated in a solution to give H positive ion. While a weak acid is something which is not completely dissociated or only partially dissociated. Strong electrolyte which is completely dissociated, weak electrolyte which is not completely dissociated. Fine. For example, we have one example where we know that this is acting as a strong acid. HCl is acting as a strong acid. Here is acting as a strong acid. Now let me give you the example of a weaker acid. So if you see this acid, which is acetic acid or ethanoic acid, if you dissolve this in water, this goes and takes up the proton, pushing these electrons onto oxygen, and what you get is CH3, C double bond O, and O negative. Okay, O negative, or the acetate ion, plus hydronium ion, hydronium ion. So this arrow is the arrow of reversibility, and it's more towards the more towards the product side. So acetic acid or ethanoic acid is a weaker acid. Now these terms, strong acid, weak acid, they are qualitative terms, like relative terms, but to have a much more profound understanding of strong and weak, we need to quantify this. Quantify the terms strong, weak, etc. using some measure. So we'll explore this in the subsequent lectures, how we can quantify the acidity or the acidic strength of an acid. Thank you.